This is the remaining problem we had left yesterday?
Well, I chose 3.
Okay.
You just think
Okay, guys, so looking at this problem with you, we're supposed to find the region bound between these two curves and then find the area of the region bound between the two curves. So what I would like to do first and foremost is I prefer functions y in terms of x. That's just easier for me to think about. Both of these, we can do that with. So that would be my first step over here. I'd say this is simply y is equal to 1 minus x. That's a linear equation with slope -1 and y-intercept 1. Easy to graph. Over here, I would have to say, well, y to the 1/2 power is equal to 1 minus x to the 1/2. And then I would have to say that's the same thing as the square root of y equals 1 minus the square root of x. And then square both sides. So y is equal to the group 1 minus the root of x squared. Okay. Now, when I think about these two graphs, it might be somewhat problematic to try to graph the second one on your own. Now you could get a pretty close graph because we already know the x and y intercepts of this graph are 1 and 1 as well. Same thing as this one. So automatically I am certain, even if I didn't know how to graph them, I know that the first one has an x-intercept of 1 and a y-intercept of 1. The second one has an x-intercept, so if I let y equal 0, x is 1. If I let x equal 0, y is 1. I know it has x and y-intercepts at 1 and 1 as well. Now, what I don't know about the second one is whether it goes down or above in this region. Could I plot out a point and find that out? Sure I could. Also, you could go to your calculator and I'll say, okay, graph this on here. My first equation, of course, 1 minus x. Whoops, not 1 minus finance. 1 minus x. Second equation is the group 1 minus the root of x. I close the root of x, close the group, and I square it. So now, whenever I'm thinking of this, you might graph it on Zoom 6, Zoom 4. I'm going to try Zoom 4. That is really a sufficient graph for what we need. But I bet you're thinking, well, I'd like to see a better graph. So would I. So if you want a better graph, I'll go Zoom Box and say, I want to see my graphing screen start at about -0.5, well, I'll say 1.5. And I'll bring it over till x is 1.5. And then I'll bring it down till y is about a -0.5. That's going to be my new graphing screen. I hit enter. Gorgeousness. There's your linear equation. There's your square of a square root equation going in through there. So I can easily see the area of this region is going to be contained within x equals 0 and x equals 1. And it's going to be the top curve is the linear function. The bottom curve is going to be the curve involving the square root. So I can say, if I just sketch this on my sheet of paper, it's going to look something like this.
So it would be perfectly legal for us to use the calculator and then just draw what we see?
Absolutely. Absolutely.
I kind of felt like that would be cheating or something. No. I didn't know if there was some way to do it with just math.
You need to use your resources.
So, I think you're the first math teacher.
Wow. So I know that the thickness of my rectangles is going to be a change in the x-axis. And I can say, well, okay, the area of this region. You need to say where the area begins in terms of x to where the area ends in terms of x. Well, that's 0 to 1. And then you say, well, the height of each rectangle. The height of each rectangle, top function minus bottom function. So I'll say it's the integral of the group top function is this, the linear function. So I'll say 1 minus x minus the bottom function, which is this group, 1 minus the root of x quantity squared. All of that is the height of each rectangle. And I know the width of each rectangle is delta x, which becomes dx as we put infinitely many of them in there. So I'll say, okay, that's my integration formula. At this point, hopefully you're saying, well, that is not acceptable within an integration formula. I don't know how to integrate the group 1 minus the root of x to the second power. We don't. You have to algebraically simplify it out, FOIL it out first. So I'll just go over here real quick. 1 minus the root of x times 1 minus the root of x. We know that that's going to give us 1 minus 2 root of x plus the root of x times the root of x plus x. So I'll know I have this minus that term in there. The area formula is going to be the integral from 0 to 1 of the group. I'll put it in descending order of x. I have a negative x minus an x. Well, actually, I think I'm going to show my work a little better. 1 minus x minus the group 1 minus 2 root of x plus x. All of that with respect to x. So now I'll show my canceling. I know that negative x minus an x, it's going to be negative 2x. And I have now taken care of those two. Then I go to the root of x. I'm going to have a negative 2 on the root of x, so plus 2 on the root of x. 1 minus 1, 1 is gone. So I have the integral of this group, and I'm integrating that with respect to x. Okay. Power rule says this negative 2x becomes negative 2x squared over 2, negative x squared over, sorry, not negative x squared over 2, just negative x squared. And then this 2 on the root of x, we know that that's 2x to the 1/2. Whenever we integrate that, that's going to be 2x to the 3 over 2 times 2/3. So I can say, well, that's going to be 4/3 x to the 3/2. I'm evaluating this from 0 to 1. The nice thing about evaluating this at 0 is I know they're both 0, so I can pretty much ignore it. When I evaluate at 1, 1 to any power is 1, so I'll say I'm going to get a negative of 1 when I plug it in for the first term, plus 4/3 times 1, plus 4/3. Negative 3/3 plus 4/3, final answer, 1/3. Okay. So that one, not bad at all. The next one we don't need our calculator for. I'll just say for number 40, we should be very comfortable working this problem without a calculator. And in order to emphasize the importance of doing it without a calculator, I would say exact answers only on problems involving trigonometric functions. So you say, well, then I need to know what the graph of the tangent and the negative tangent looks like just from heart. Yes, we should. So the tangent function, we should know, starts at negative pi over 2 and ends at pi over 2. And if you have any trouble with that, the unit circle helps you figure it out. Everything goes back to that gorgeous unit circle. When you think of negative pi over 2, we know that the coordinate there at negative pi over 2 is 0, negative 1. The coordinate up here at pi over 2 is 0, positive 1. So I can say, why does the tangent function start at negative pi over 2 and end at pi over 2? It's undefined at both of those values. Tangent is sine over cosine. Sine over cosine, undefined at negative pi over 2. Undefined at pi over 2. So I'd say, okay, if this is negative pi over 2, I know the tangent function is going to have an asymptote there. It will have another asymptote at pi over 2. And the only other point I really need here is, what about at 0? At 0, you know your cosine is 1, your sine is 0. The tangent of 0 is 0 over 1, 0. So then I could say, what's the sine of the tangent function as I go through that first quadrant? As I go through the first quadrant, the tangent function is the ratio of sine to cosine. So it starts off very small because the sine is small, the cosine is large. At pi over 4, it becomes 1. Because at pi over 4, you know both the sine and cosine are the same value. So I'd say that's another critical point here. Pi over 4, the value is 1. And then as I go on up beyond pi over 4, using limit notation, I could say the limit as x approaches pi over 2 from the left of the tangent function is infinity, because literally here the y value would be like 0.9 repeating, the x value would be a billion zeros repeating, then a 1. That's going off to infinity. So I could say gorgeousness looks like that. The fourth quadrant from 0 to negative pi over 2, same thing, except it's going towards negative infinity in this case. At negative pi over 4, your tangent is negative 1 because sine is negative square root of 2 over 2, cosine is positive square root of 2 over 2. So I'd say it's just going to be like this. The tangent is an odd function. It has origin symmetry. So I'd say, okay, I have that drawn here. That's the positive tangent function. Say, graph the negative tangent function. We know that that's just the exact opposite of this. When you take the negative of a function, you reflect it about the x-axis. So the negative tangent function would be starting high and finishing low here. So I'm looking for, in this problem, in number 40, the area of the region enclosed by the curves tangent x, negative tangent x, and x equals pi over 4. X equals pi over 4 is the vertical line at pi over 4. So this is the region I'm looking for. I know, again, tangent of pi over 4 is 1. So this point right here is pi over 4, 1. This point down here, pi over 4, negative 1. So I'd say, what's going to be the easiest way to evaluate this function? Easiest way, clearly, is to draw your rectangles vertically, because throughout this entire region, yeah, you can really see that rectangle in there. Throughout that entire region, you know that the top of the rectangle is the positive tangent function, the bottom of the rectangle is the negative tangent function. So I could say, okay, the integral from where this region begins at 0 to where this region ends in terms of x at pi over 4. So I'd say the area is equal to, let me erase this previous problem so we don't get that confused with it. So the area is equal to the integral from 0 to pi over 4 of the top function, the tangent of x, minus the bottom function, which is the negative tangent of x, dx. Okay. Now, a couple things I could do here, and I just noticed it's going to be the same way either way. I could just say, well, okay, go ahead and subtract minus a negative. That's 2 tangent. You could factor the 2 out in front. That works. I could have also said, due to symmetry, this is equal to 2 on the root 0 to pi over 4 tangent x dx. So when I was thinking, so you could just use this and say, well, when you subtract, of course, it's 2, and that 2 can factor out in front. Yes. When I see this, though, I wasn't really thinking of that. I mean, it can be, but I was thinking inside of this, because this function is going to be the same above and below the x-axis, I was saying, or I was thinking to myself, why bother with that bottom region? Just find the area of this top region. And that would be saying, well, your top curve is tangent x, your bottom curve is 0, but again, I want the area of the entire region, so what do? I need to double it. So by symmetry, you could get to this, and also just by subtracting a negative tangent, you get to that either way. So symmetry and the function works out to be the same thing in this case. Sometimes you're going to need to use the concept of symmetry to evaluate a problem. It might be ridiculously difficult to find the area of the entire region, but pretty easy to find it, half of it, and then double it. Okay, so I have 0 to pi over 4 of the tangent function. I could say, well, tangent function is not something we can easily integrate. Just because we can derive the tangent function doesn't mean we can integrate it. Derivative of tangent is secant squared. Integral of tangent, not secant squared. So you say, what do we do?
Sine over cosine.
Yeah. And then you can do a u substitution. U is equal to cosine x. So du is derivative of cosine is negative sine of x with respect to x. So I need to see a negative sine of x dx in there. I don't. So I put it. And I have to make up for that by also multiplying the outside by a negative. So now I have negative 2 on the integral of negative sine x over cosine x dx. Okay. Now, if u is cosine x, then I can say I also need to evaluate u at 0. Cosine of 0, we know is 1. U at pi over 4. Cosine pi over 4, we're supposed to remember, is the root of 2 over 2. So now I can take all of this information and write a refined problem. This is going to lead me to negative 2 on the integral, not 0 to pi over 4, but 1 to the root of 2 over 2. And this is going to be on the negative sine of x dx canceled out, became du. The other is 1 over u. 1 over u du. We know what to do. That's the natural log of u. And I don't want to put the plus c since this is a definite integral. I'll have negative 2 natural log of u. No need to put the absolute value because both of our limits of integration are positive. So I'll say, okay, this is negative 2 times the group. Natural log of the square root of 2 over 2. Minus the natural log of 1. But hopefully you remember, well, the natural log of 1 is 0. So, because e to the 0 power is 1. So that last term doesn't contribute anything. So I would say, well, my answer is just negative 2 natural log of the root of 2 over 2. Now, I bet I know what you're thinking. You want to move this coefficient up as an exponent. Yeah. So you'd say, okay, the fact that it would be a negative exponent means I can take the reciprocal of what's on the inside, and this is going to be the natural log of 2 over the root of 2 to the second. And then you know what to do with that. You just say, well, 2 to the second is 4, square root of 2 to the second is 2. This is nothing more than the natural log of 2. 4 over 2 is 2. Natural log of 2 is what we would do. Yeah?
In the problem, it actually says x equals 2 to x. Is that supposed to be that?
Oh, I specifically switched. Oh, wow, it does.
So wouldn't that just be 0?
That's horrible. X equals tangent. That's a typo. That's
Are you
a
sure?
typo.
Because it would just be x equals 0.
No, it's a typo. I promise you that. Boy, it does though, doesn't it? Yeah.
I just kind of ignored it.
Yeah, I promise you, it's supposed to be y equals tangent x and y equals negative tangent x. So if they wanted to put it as a relation, they would have said x equals tangent y. They don't want x equals tangent x, I promise. It's a Rogowskiism. Okay, so the last problem. This is one of those, like I did in the homework problems. I think you'll notice when I worked like a homework problem like number 35, I took the weak way out and said, yeah, I know it's x equals y cubed minus 18y and y plus 2x is 0, but I'm going to treat it as y equals x cubed minus 18x and x plus 2y is 0. Why did I do that? Because I can. And you're like, is he being sarcastic? No, not really. Because I need you to see, if it's easier to think about something with a variable swapped up, variables are just assigned letters to represent some situation. So if you switch them around, you switch the other one, it's the same thing. It might be a different representation graphically, but the area is going to be the same. So I can say, yeah, that's just the smarter way to do the problem. Certainly more efficient. So when I look at 42, and you think, well, x equals the sine of y. We know y equals the sine of x is a cyclical function like this. Well, x equals the sine of y is just going to oscillate up and down on the y. I don't want to draw that. I'm not going to. So what do? I interchange the x and y values. As long as I do it in both equations, completely, utterly legal. So I'll say, smart way to work this problem is to say, just imagine that says y equals the sine of x. Your second one, you must switch all variables. So this is y is equal to 2 over pi x. Okay. So if I graph my y equals sine of x function, I know that the sine function, sine of 0 is 0. So again, I'm just thinking unit circle. Sine of 0 is 0. Sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. Ooh, that flattens out a little too much. I think this is all we're going to need. Let's see. So I can say, of course, if I wanted to keep on going, it could go down and back up again. I also want to graph my y equals 2 pi x function. If you think about that, y equals 2 pi x, 2 over pi x, not 2 pi x. I can say, well, the x values I think are going to work are when x is negative pi over 2 and when x is pi over 2. And I think you'll see pretty quickly, yep, these are the ones that work. At x equals pi over 2, the y value here, 2 pi times x, becomes 2 pi times x value, pi over 2. Please notice, when x is pi over 2, this function is 1. When x is negative pi over 2, this function would become negative 1. So what I know is that the linear function I'm dealing with has these same points, but it is a linear function. So I'll say, well, construct a line between those 2 points, and I get that. Okay, now, it would be wise if we're smart in evaluating this integral. If I just said, tell me a function that represents the entire thing as it is. If I want to integrate with respect to x and say, well, here's my rectangle. In this first region from negative pi over 2 to 0, the linear function is on top, the sine function is on the bottom. But from 0 to pi over 2, the linear function is now on the bottom and the sine function is on top. That's a problem. So one thing you could do is just make the work easier on yourself. Due to symmetry, and what symmetry am I talking about? Both of these functions are odd functions. The sine function is odd because the sine of negative x is the negative of the sine of x. Same thing with a linear function. All lines, if you change the sign on x, it changes the sign on y. They both have odd symmetry, so this region is equivalent to this region. So I would say, due to symmetry, the area is equal to twice the integral from 0 to pi over 2 of the top curve, the sine of x, minus the bottom curve, the linear function, 2 over pi x, with respect to x. So then you're thinking, okay, this is going to be pretty easy. Yep. I'll say it's going to be twice. Integrate the sine. I can say, well, the integral of the sine is going to be negative cosine integrate 2 over pi x. Remember, 2 over pi is just a coefficient. So that's going to become x squared. Divide this by 2. I get minus 1 over pi x squared. And then I evaluate this from 0 to pi over 2. When we evaluate at pi over 2, I'll say, okay, this is going to be twice. When I evaluate at pi over 2, I'll get negative cosine of pi over 2 minus 1 over pi times pi over 2 quantity squared. That's all the first one. From that, I would subtract. When I evaluate all this at 0, it's going to be minus the negative cosine of 0 minus 1 over pi times 0 squared. Okay. Cosine pi over 2, the x value on the unit circle pi over 2 is 0. Nothing there. So I'll have left minus 1 over pi times pi squared over 2. This pi is going to cancel out with one of those pi squareds. And so I'll say I'm going to have left negative pi over 2. So I still have my 2 on the outside that I'll keep. Oh, thank you. Because the 2 is squared. Thank you. So I still have my 2. I was just thinking going ahead and multiplying by that 2. That's what I was doing. Negative pi over 4 for that term.
Wait, wouldn't it be
1.5 pi.
wouldn't it be pi squared still?
No. That pi canceled out.
Oh, I'm sorry.
So pi canceled out pi squared, left pi. But I still do have the 2 squared for the 4 and the negative out in front. Then I can say minus a negative 1 plus 1. All of that's just a 0. So I have 2 times this group. When I distribute the 2 through, I would say my final answer is going to be 2 minus pi over 2. That's what I would do. Okay. Now I think I know what you're thinking. You're thinking, well, that's not bad at all. It's not at all. So next section, and we'll do the next section in the span of about 15 to 20 minutes. Which leaves the rest of the class to look at 6.3. And we'll be doing it next class too, I'm sure. Yes. Well, bad for me, maybe not for you.
Does that mean it's easy?
No. I wouldn't say it's easy if you get it. And
Aren't all things like that?
the reason it's bad for me is it involves a lot of graphing and being able to represent situations.
I don't like graphs.
Yeah, I don't like drawing graphs. Graphs are fine, but when I have to illustrate,
I think you might like these. They're starting to grow on me, and I hate drawing, and I don't mind it. Okay, but section 6.2. Let's say, guys, I give you some constant function. I'll say this right here. Now, obviously, this is going to be an extremely easy start, but I'm trying to prove a point here. So I'll say, well, okay, I'm going to tell you the area of this region under this curve, that's just a flat line. What if I say the area of the region is 80 square units? And that this region starts at x equals 0 and ends at 010. So if this is some curve f of x on x equals 0 to 10, whoops, inclusive, then obviously if I said, okay guys, what is the average value of this function f of x between 0 and 10? Hopefully you'd look at me like, please don't ask that, that's too lame of a question. The average value is 8. Why is it 8? Because you say, well, I know that the height is always 8. So the average height is always 8. But the point is, where are you getting that from? You're saying, well, I'm just taking the area under the function divided by the change of the x values of the function. That gives me the height of the function. I know area is length times width. The width in this case is the height. So I just say 10 times 8 is 80. Yes. Okay. So that same logic applies if I have some function that does this between 0 and 10. So if I say, now I want you to find the average height of this function between 0 and 10, well, it's a lot harder than this case because I don't have that constant height. Same principle applies though. If I can find the area under this function, divide it by the width that the function covers, it's going to give me the average y value every single solitary time. So to sum up what I want us to know out of this section, the average value of a function is equal to 1 over b minus a on the integral from a to b of f of x dx. This gives you the average y value of the function f of x over some interval where f of x starts at a, ends at b. And you say, well, that's 1 over the change in the x variables. This will give me the area under the function from a to b. So very, very straightforward concept here. Now, in order to just show you the problems I want to work with that concept, you only have 4 assigned problems. I'll look at 3 of the evens through that same section. Number 40 here. You have f of x is x cubed. And you're asked to find the average value between -1 and 1. So that's not going to be bad at all. The average value of x cubed between 1 and 1. Now, if you graphed out f of x equals x cubed between -1 and 1, you know x cubed looks like this. I am already 100% certain, since this is an odd function, as soon as I give you a negative x value and that positive x value is the same thing. So what if I said, I want you to tell me the average value from -10 to 10 or -1000 to 1000? The answer is always 0. Why? It's an odd function. It goes down every bit as fast as it goes up for the positive x values. I am already certain the answer to this question is 0. But let's show it using calculus rather than just logic. So you'd say, well, okay, the average value of the function should be 1 over b minus a. 1 minus negative 1. On the integral, negative 1 to 1 of f of x, x cubed, with respect to x. So this is going to give me the span of the x variables is 2, so whatever I get, I'm going to multiply by 1/2. And I'll say this is 1/2 times the group. When I integrate this, I get x to the 4th over 4, evaluated from negative 1 to 1. And now I see why, yes, I'm going to get an answer of 0. Because it doesn't matter whether I plug a 1 in or a negative 1 in. I'll get 1/4 minus 1/4. Top limit minus the bottom limit. And I'm getting, well, 1/2 times 0 is 0. Which graphically, we already knew 0 had to be the answer. Okay. Now you're thinking, well, that was almost annoyingly easy. Okay, I'll look at 44. Now, most likely, I would not insult your intelligence and give you a function that I ask you for the average value, which you could just look at and tell me the average value. I don't want you to think badly of the way I think of you, so I wouldn't do that.
Oh, we wouldn't feel that way at all.
This is probably a more, I started saying more better. This is probably a more realistic example of what I would expect. It's certainly not hard though. We have f of x is the sine of pi x, the sine of pi over x, divided by x squared. And I'm asking you, what is the average value of this function on the region between 1 and 2? So, quite honest, I don't know what the sine of pi over x squared looks like between 1 and 2. Nor do I really need to know what it looks like. Because the average value function tells me that if I want to find the average value of this function over this region, every single solitary time, I'll take 1 over b minus a. That gives me the change in the x values. So we're going to divide by the distance it covers, which in this case is just 1 unit. On the integral, find the area under the curve from 1 to 2 of the sine of pi over x squared with respect to x. Now, at this point, it's not that easy because you say, well, you have something other than x inside the sine function. That should be a clear indicator. A u substitution is probably in order. So I'll say, well, if u is pi divided by x, pi divided by x is probably more easily written as pi x to the negative 1. Then you can see, well, du, the negative 1 would come down in front, negative pi x to the negative 2 with respect to x. So du is negative pi over x squared dx. I need to see that inside of this problem if I'm going to do a u substitution. Well, I see the x squared dx in there. That's good. So all of this is going to become du, but I also need to see a factor of negative pi. I can put a negative pi in there with it if I remember to divide the outside by negative pi as well. So I'll say all of this times 1 over negative pi on the outside. Okay? I had to do that in order to force this u substitution. So now all of this becomes du. And I have my negative pi on the outside along with my constant, which is just 1. At the same time, I'll change the limits of integration. So the previous limits of integration were 1 to 2. I need to evaluate u of 1 and u of 2. u of 1 becomes pi over 1, obviously that's still pi. u2, pi over 2, that's what it is. So my new limits of integration, instead of 1 to 2, it's pi to pi over 2. On the outside, the average value of this function is going to be given by 1 over 1 times 1 over negative pi. That's just 1 over negative pi. I would prefer to say negative 1 over pi. On the integral from pi to pi over 2. What's inside? All of this becomes du. All of that becomes just the sine of u. Sine of u du. Now we can integrate and say, well, the integral of the sine is the negative of the cosine. Now, that's actually nice because I'm going to say the negative of the cosine is going to cancel with this negative out here. And I'll just have 1 over pi times the cosine of u evaluated from pi to pi over 2. So I eliminated the negative with the negative I had outside. And so I'll get whatever answer I'm getting. I know it's going to be divided by pi. And cosine pi over 2, cosine pi over 2 is 0, minus the cosine of pi. Okay, so minus cosine of pi is negative 1. So minus a negative 1 is going to be plus 1. Our final answer here is just 1 over pi. That is the average value of this function. Now, if you're thinking like me, that's kind of a cool problem. One last one in this section. And just to show you that the homework is ridiculously quick and easy, I don't think I have it scanned and posted yet. That's it right there. 37 through 47, about half a page. Looking at 46. We have f of x is equal to 1 over x squared plus 1. Hopefully, every single solitary time you see that function, hopefully in your mind, oh, that's the integral of that is the inverse tangent function. That's something we've got to have ingrained in our minds. The integral in this problem most definitely will be inverse tangent. So I say, I'm trying to find the average value of 1 over x squared plus 1 from negative 1 to 1. And I can say, well, okay then. I'll say the average value is equal to 1 over b minus a. Again, that's going to be 1 over 2. The distance in the x values is 2 units. On the integral, negative 1 to 1 of 1 over x squared plus 1 dx. This one's quicker than the last one because there's no substitution needed directly. That's an inverse tangent function. So I'll get that the average value is 1 over 2 on the group inverse tangent, or times the group inverse tangent of x, evaluated from negative 1 to 1. Now, what you have to remember about the inverse tangent function is that the inverse tangent only exists if you restrict the tangent function from negative pi over 2 to pi over 2. So this is literally asking you, when it says inverse tangent of 1, it's saying, when is the tangent function 1? Technically, you could say, well, the tangent function is 1 at pi over 4, but it's also 1 at 5 pi over 4. Why can't I use 5 pi over 4? It's not in the domain of the tangent function to where the inverse tangent function exists. It has to be between negative pi over 2 and pi over 2. So, since I can say the tangent of pi over 4 is 1, the inverse tangent of 1 is pi over 4. So I'll get 1/2 inverse tangent of 1 pi over 4 minus the inverse tangent of negative 1. So you ask yourself, when is the tangent function negative 1 in between negative pi over 2 and pi over 2? That's at an angle of negative pi over 4. At negative pi over 4, we know our cosine square root of 2 over 2, our sine's the negative square root of 2 over 2. Thus, the tangent of negative pi over 4 is negative 1. So the inverse tangent of negative 1 is negative pi over 4. Please remember, every single inverse trig function, it's simply an angle. So you say, I know I'm looking for the angle when the tangent function is negative 1. That angle, negative pi over 4. This is going to give me pi over 4 plus pi over 4, which is pi over 2. But then the outside is going to knock it back down to pi over 4. Okay? Now, I'll probably better erase the whole board for 6-3. 6-3, quite often people may think is the hardest section that we encounter throughout the year, especially if you have trouble visualizing stuff. So my goal is to try to make it absolutely as clear as I possibly can. Please let me know if I achieve that. And if not, I can work with you one-on-one to get it achieved. I think it is certainly possible, but this is an important section, and I need to make sure that we do get it. What we're looking at is volume in this section. Oh, finding. Now, what I need to convince you of, first of all, and I'll just write it out here, to find volume, of any object, we break it down into a component infinitely thin cross-section. I'll say we find volume of an arbitrary infinitely thin cross-section. Okay, now, then we sum up all of the cross-sections throughout the object. So then we'll sum all these cross-sections. And how many cross-sections are there? Infinitely many of them. Can we do that? Yeah, that's what the integral does. It's a summation formula. Sum all these infinitely many thin cross-sections. So sum all these cross-sections from where the object begins to where it ends. Now, so if we think of volume within this context, hopefully it's going to make some sense. Now, let's talk about some things we already do without really thinking about it. Like if I say, okay guys, volume of a cube. You'd say, volume of a cube, or volume of a rectangular solid, length times width times height. What are you doing whenever you're finding the volume of that rectangular solid? Well, quite honestly, whenever you say length times width times height, and you say, okay, so if I have some rectangular solid here, what I could do is say, well, I know that the area of the base could be the length times the width. Okay. So I could say, the area of the base would be length times width. What if I said, let's give that base an infinitely thin thickness? And say, well, if I took a cross section of some region in through here, and then I said, okay, now let's magnify that cross section throughout the entire object. All you're doing every single time when you find volume is you say, it's the area of the face times the number of faces, which in this case is h. Length times width times height. That's why. When you look at area of a cone, there's a reason area of a cone is pi r squared h. It's because, so volume of a cone is pi r squared h. Because all it is area of the face of the cone is area of a circle. You'd say, hey, area of that is pi r squared. How do I go from area of the face, a cylinder, sorry, I said cone, I'm sorry, cylinder. Yeah, bad. So area of a cylinder, pi r squared h. If I took the face apart of it, it'd look like this. Then I'd say, well, how do I go from that to the volume formula? You just multiply by whatever the height of the object is. So you say the pi r squared h. That same logic that's used in that, it's going to be used in our problems. Let me show you what I mean. I want us to find the volume of solid obtained by rotating y equals the square root of x about the x-axis from x equals 0 to x equals 1. Okay, so when I think about this, I can say, well, draw your square root function. Square root function looks like a half parabola there. So I could say, well, okay, this is from 0 to 1. I'll go ahead and label it here. That's my 1. Now, what am I doing with this? My axis of revolution is my x-axis. So I take this object, which is the square root of x, I need to rotate it about the x-axis. So when I do that, I can say, well, okay, it's going to look something like this. So my region here it's going to look like this. So it's just going to be a bowl turned on its side. But now it's a solid. Everything inside of it is part of it. So I can say, okay, how do I account for this volume formula? Here's what I need you to do every single time. I like to think of it as you take like a very sharp blade or something, and you're just going to take a Ginsu knife and cut into the region, an infinitely thin cross section. I know that every single cross section from here all the way to the end is going to look something like this. Now, I'm not putting hair on a face. I'm trying to show that it has a certain thickness. Usually people say, why are you drawing hair on it? I'm not. I'm trying to show that it does have an arbitrary thickness, however thick you cut it. Now, if I ask you to label this, guys, that thickness, the thickness of any cross section, is it going to be a change in y or a change in x? Excellent, excellent. So it's a change in the x-axis. So that's delta x. Okay, we'll get back to that. Now if I say, okay, tell me what the formula for the area of any of these cross sections would be. I'd say, well, the area of any particular cross section within this region. And it might help to come back over here. You say, where is he getting that center point? The center point is the axis of revolution, the x-axis. So every single one of your radiuses in these regions That's going to be my R value. What is the R value? It's the length from the x-axis to my curve. That length is y equals the square root of x. So I can say this is nothing more than the square root of x for every single solitary one of those in there. Then we go over here and say, well, I know area of a circle is pi r squared. So the area of every one of these cross sections is going to be pi times the radius squared, pi x. Now, hopefully you're thinking, but John, you don't want the area of the cross section, you want the volume of the cross section. Right? That's where this comes in. The height of every one of those cross sections is going to be delta x. So I could say volume of a particular cross section is going to be pi x, that's the area of the cross section, times the height, delta x. Okay. Are we all right so far? Now, all you're doing from here is you take this to what I was saying here. So we find the volume of an arbitrary, infinitely thin cross section. Done. Now, I want to sum, in other words, integrate all of these cross sections from where they begin to where they end. Now, in terms of what? X or Y? In terms of x, that's the thickness. I have to say, in terms of x, where do these begin? Where do these end? From 0 to 1. So I'd say, okay, the volume of this region of revolution, I'll say the volume in terms of x is going to give me the integral from where it begins to where it ends, 0 to 1. My formula is going to be pi x. As I make infinitely many of those, delta x becomes dx. Pi x dx. Oftentimes, you're always going to have a pi in these, so most people just go ahead and factor it out in front. Doesn't matter either way. I'll leave it in there since I already have it in there. I integrate, and I'll say, well, this is going to be pi x squared over 2. Evaluate it from 0 to 1. When I evaluate it at 1, of course, I'll get pi over 2. When I evaluate it at 0, I get 0. So I just get pi over 2 as my answer. The area of this region of revolution here, pi over 2. Sorry, volume, not area. The volume of this region of revolution is pi over 2. Are we okay with this introductory problem? Okay.
So if it's an infinitely small slice, I mean, is it essentially area?
Well, I like that you're thinking that. If you take a volume that's infinitely thin slice, it essentially is area. But if you sum up an infinitely amount of areas, you get volume. That's why the change in volume with respect to time is an area function. Okay. Next problem. Now, what I want to do today, hopefully, is show you an example revolved about the x-axis, revolved about the y-axis, revolved about a different horizontal axis, revolved about a different vertical axis, and revolved about a diagonal line. All of those create their own problems. So the second one here, I'll say, find volume of solid revolved, a solid revolution, from region bounded by y equals x cubed, y equals 8, x equals 0, and then I'll say about y-axis. The y-axis is your axis of revolution in this problem. So So I need to graph out my region. Now, I need to graph the bounded region. I don't necessarily need to graph the entire volume of the solid of revolution. That's where we can really see what the arbitrary cross-section looks like without drawing the entire object. So I'll say, okay, with that in mind, I know y equals x cubed looks like this. Y equals 8, so a horizontal line at y equals 8. And then x equals 0, that activates the y-axis. X equals 0 is the y-axis. So what I need you to see here is that the region bound by all three of these curves is this region right through here. Now, what am I doing to this region bound between these curves? I'm rotating this region about the y-axis. So you just say, oh, okay, if I rotate this, then that solid is going to go all the way. This really is just a bowl. Now, if I ask you, and could you draw out the entire, if you wanted to, you certainly could. There's no reason to. I would like to draw an arbitrary cross-section. That arbitrary cross-section, we need to see that it would be horizontally cut. You'd have to cut into it this way. It would make no sense, as in the last problem, I did a vertical cut where the thickness was in terms of x. That would make no sense whatsoever in this problem. You're not going to cut it that way. You have to cut it this way because it's revolving about a vertical axis. So I'd say, okay, each of my cross-sections look like this. Now, something you might want to make mental note of here. If you're revolving around the x-axis or any horizontal axis of revolution, notice the thickness is going to be delta x. Makes sense. X-axis, delta x. If you're revolving about the y-axis, the thickness of all of your cross-sections is going to be a change in y. Okay? So if you say, well, okay, I need you to tell me a formula for the area of the cross-section. You say, well, okay, I got it right here. Absolutely terrible. You cannot say that the radial length is x. That doesn't work. Why doesn't? You have to give it to me in terms of y. Because that's the thickness of your cross-section. So you say, well, that's no problem. If y is equal to x cubed, that means x is equal to the cube root of y. So the distance from the axis of revolution to any point on any cross-section throughout this entire region, it's going to be the cube root of whatever the y value is. So I could say, okay, cube root of y. Therefore, the area of one of these cross-sections is going to be pi times the cube root of y squared. Cube root of y squared, that's going to just be y to the 2/3 power. So I'll say pi y, hey, that has a nice ring to it, pi y. Pi y to the 2/3 power. So your volume formula, pi y to the 2/3 dy, or sorry, delta y for now. So any arbitrary cross-section is going to be pi 2/3 y, sorry, pi y to the 2/3 times delta y. That's the thickness times the area of any cross-section for the volume of the cross-section. Now we just say, okay, for the volume of this entire solid, it's going to be the volume in terms of y, because it has to be. And you'd say, this has to be in terms of where y begins to where y ends. So y equals 0 to y equals 8 of this formula pi y, and this time I am going to go ahead and factor out the pi, because we can. So pi y to the 2/3 dy. When I integrate the y to the 2/3, it's going to become y to the 5/3 times 3/5. So I'll say this is pi times 3/5 y to the 5/3 evaluated from 0 to 8. I know when I evaluate it at 0, it's going to be 0, so that doesn't amount to anything. When I evaluate it at 8, that's not going to be too bad. Cube root of 8 is 2. 2 to the 5th power is 32. 32 times 3/5, that's going to be 96/5. So I can say this is 96 pi over 5. When I evaluate it, 0, again, doesn't amount to anything. So this is final answer. The volume of that rotated region of the object, of the resulting object, would be 96 pi over 5. Are we okay with this? Okay. I don't see too many blank looks. Yes. This is usually, people think, bad stuff.
I'm just having fun using the draw stuff.
Okay. A next step up in difficulty. So far, both of the and you might want to label both of these problems. It's what's referred to as the disk method. Disk method is where there is no interruptions from your axis of revolution. It's just the entire object. Okay. What if we up the difficulty level and say, what if I want to hollow out this region and say, I don't want any of that region there. What if I have a curve that goes into the interior here, and I want to find only the volume of that exterior region? Ah, this is what's called the washer method. So the first two were disk method. This one's going to be washer method. And in order to show you a good washer method problem, I'll say, okay, think about these two curves. I want the region between y equals x and y equals x squared. Rotated about x-axis. We want to find the volume of the resulting solid. So I particularly gave us a region that's pretty easy to find. Y equals x. I'll say, okay, straight line, slope of 1. Y equals x squared. We know when I plug in a 1, the y value is also 1 here, but a parabola starts off U-shaped, so it's actually going to be the low function throughout this entire region, and then it would overtake after that. But this is the region enclosed. So what I want to do is take this region and revolve it about the x-axis. Now, fortunately for me, this is where, I would have some significant difficulty trying to draw this object. We don't have to. All you have to think about is what is one cross-section going to look like. And I could say, well, I know every single cross-section is going to have an interior part that I don't want to account for, and then an exterior part that I do want to account for. So I'll draw it like this. Now, I never understood why to draw it like this, but a previous student said I absolutely have to draw that to give it some three-dimensionality. I don't know. doesn't make sense to me. I'm not. Yep.
Because you can't see the outer edge, you should see the inner edge.
Yeah, I guess. Yeah.
So,
Okay. So as long as you can see, I'm trying to give it some thickness there. That's what that's for. Okay. So in this washer, I'm trying to think, what do I need to account for? It's this exterior region that I want. That's where the volume's at. I want to hollow it out in my formula because that's in actuality, that's what happens. I don't want the outer, I want the, I don't want the inner, I want the outer region. So I could say, well, this inside region, I could find the area formula for it, and I could say, well, that's just going to be from the axis of revolution to the inside curve, which that curve is x squared. So I'd say this is x squared. The exterior radius here is just x. And how do I know I wanted these in terms of x? Because the thickness of each of my cross-section is a change in the x-axis. So I would say the area of the face of a washer is going to be pi times, it's going to be the outer radius, and if you just want a general formula, pi times outer radius minus pi times the inner radius. And then you might say, well, hey, instead of putting pi with both of those, why don't you just factor the pi out and say pi times the outer radius minus the inner radius? Why, yes, that's what I would do. So I'll say the area formula is going to be pi times the exterior radius, or the outer radius, x. Ooh, and it's pi r squared, ooh, me. So pi times x squared minus x squared squared. So please make sure where I'm getting that. This makes it look misleading because you say, oh, he's calling the inner radius the outer. No, I'm not. This is the radius x, but our formula says pi r squared. And I'll say that's the outer radius minus the inner radius where it's x squared, and then you have to square it as well. So I'd say, well, this is just going to be pi times x squared minus x to the fourth. Pi times outer radius squared minus inner radius squared. And then, so the volume of a cross-section is just pi times x squared minus x to the fourth times the thickness of the cross-section, dx, or delta x. So, hopefully you see where I'm going with this. You'd say, the next step is just to, in order to find the volume, I need to sum every one of these conceivable possible cross-sections from where the cross-sections begin in terms of x to where the cross-sections end in terms of x. They begin at x equals 0, they would end at x equals 1. So the volume in terms of x of this region is going to go from x equals 0 to x equals 1 of pi x squared minus x to the fourth. I'll factor the pi out. Dx. Every single time, your integral formula is going to have a pi probably on the outside is best. And this is going to be the outer radius squared minus the inner radius squared every time. And then you'll say, okay, so the volume, pi times the group, x cubed over 3 minus x to the fifth over 5 from 0 to 1. This is another one of those cases when we evaluate it at 0, we get nothing. So you only have to worry about 1. I'll get pi times 1/3 minus 1/5. 1/3 minus 1/5, that's like 5/15 minus 3/15, which is 2/15. So this is going to be 2 pi over 15.
Is x squared minus x to the fourth not negative x?
No, because within the context of this problem, my values are all between 0 and 1 there, Clint. That's why. So x to the fourth is actually smaller than x squared in here, because you think, what happens when you take 0.5 and you square it? You get 0.25. What happens if you take 0.5 to the 4th power? You get 0.06125. So the x to the 4th is actually smaller than the x squared within this region. Okay? Because it's decimals. Now, I'm thinking, you're thinking, well, that wasn't too bad. Okay, let's change to a non-standard axis of revolution. So, in order to save time in the graphing, I'll just say, rotate the same region from number 3 about y equals 2. So I'll say, well, the region from number 3 was this area between x and x squared. Now I probably should put the points. This is the point 1, 1. This is the point 0, 0. But now my axis of revolution, it's no longer connected with the axis of revolution. The axis of revolution is up here. This is a horizontal line at y equals 2. So I'd say, well, if that's x equals 1, sorry, y equals 1, y equals 2 is about right here. So I'm taking this region and I'll be rotating it about this line, y equals 2. But hopefully you look at this and say, but the general principles of this problem have not changed. It's still a washer problem. The region I'm looking for is the exterior volume rotated, where I will have to hollow out this region right there. I don't want that region. That's the radius of the region I do not want. I could call that R1 if I wanted. The radius of the region I do want is down here. I could call that R2. So I could say, well, when I'm thinking about this, I know that the area of a cross-section of this region is going to be pi times R2 squared minus R1 squared. Exterior radius minus the interior radius. The only thing that makes this a little bit harder is the formulas in order to get to those. But every single time, here's what you do. If the axis of revolution, as it is in this case, is above, then we know that we're subtracting the function values in each of these cases. So, again, a cross-sectional region is still going to be going in this direction. I didn't need to make it so tall. It's still going to be going in this direction, so my thickness is still delta x. There's my R1, my R2 in there. So I'm trying to find the region of this exterior part and then expand it over the entire period from x equals 0 to x equals 1. So I say, well, okay, the area of a cross-section is pi. I need a formula for that second radial length. The second radial length is starting at 2 and going down to the curve y equals x squared. I must call that 2 minus x squared. That's the second radial length. Minus the first radial length. So I'd say, well, okay, it's starting at 2. It's going down to the line y equals x. So it's 2 minus x. And I have to square that. Now, it's extremely important, just like Clint was mentioning in the last problem, oftentimes the mistake students will make on this problem is they'll say, well, why not call it x squared minus 2? That'd be horrendous, because x squared is lower than the value of 2, I'd be getting a negative volume if I did that. You must say large value minus small value. Okay? So 2 minus... Now, what if my axis of revolution was down here? That minus the axis of revolution in that case. Okay? Which we'll do one, never fear. Okay. Yeah, go ahead.
On the Washburn on the drawing side, where is the y equals x and y x squared?
Well, so the interior one is the y, so this is my curve y equals x. This would be my curve y equals x squared down here. But the distance to that, you have to remember your axis of revolution is going through y equals 2, so you have to say, oh, so this is a distance of 2 minus x to get to that part. To get to this one, it's 2 minus x squared to get to that. Okay. So I can say, okay, this is pi times the group. If I square out this group, if you need to FOIL it, please do. It'll be equal to 4 minus 2x squared minus 2x squared minus 4x squared plus x to the 4th. From that, I'm subtracting the group. When I square this one out, I'll get 4 minus 4x plus x squared. I'm still not following, I'm sorry.
You put 2x squared. One of them should be an x to the 4th.
4
Right there.
Oh! I was like, that's not wrong. You're like, no, it's not. That one is. Sorry. Okay.
You really should be giving that extra credit.
No. So the volume, I am in all my other classes. Pi times the group, x to the 4th. I shouldn't have said that. And then I have minus 4x squared minus x squared minus 5x squared. And then we'd have our x terms, which is just plus 4x. 4 minus 4 eliminates. And then since I put volume for this one, we know, well, the thickness is going to be whatever the change in the x value is. So now, this is an arbitrary cross-section of this region rotated about y equals 2. This is the formula for that arbitrary cross-section. Now I'll say, where do those cross-sections begin in terms of x? Well, x equals 0. They end at x equals 1. So I would say the volume of this region in terms of x is going to go from 0 to 1. I'll go ahead and factor the pi out. And my group is going to be x to the 4th minus 5x squared plus 4x. Now, I think you will be disappointed with one part of this section, is that 95% of the problems are going to be ridiculously easy to integrate. It just goes back to the power rule for the majority of them. So hopefully you don't lose your substitution abilities and stuff, because this section does not test them. We'll have x to the 5th over 5 minus 5x cubed over 3 plus 4x squared over 2, which would just be 2x squared, evaluated from 0 to 1. And as with all the other ones so far, when you evaluate this at 0 into a polynomial, you'll get a 0. So the only thing you have to do is plug in the 1. When you do that, you'll get 1/5 minus 5/3 plus 2. So I know 2 is the same thing as 6/3. 6/3 minus 5/3 is 1/3. I'll get pi times 1/5 plus 1/3. That's, again, 3 over 15 plus 5 over 15 is 8 over 15. 8 pi over 15. Okay? We're going to get time to do a bunch of these. Is this making sense so far?
Yeah, I just want to make sure I understand. So the area that's covering, so it's rotating about y equals 2, so it's creating this big sort of donut thing
Right.
around y equals
Yes.
2, right?
Yeah, that's what I tried to show. The axis of revolution is y equals 2. The inside part's going to be from y equals 2 to that inside curve y equals x. The outer revolution is going to be from y equals 2 to the curve x squared as it goes around. It's always going to be the outer function involved. Okay. All right. Up next. I'll say, what if I want to take this same region so same as number 3, except my rotation region is going to be the y-axis. So you'd say, okay, simple to draw out. That's the point of me using this same region, because I don't want to stressing over the region itself. I want to stressing over the rotation. So in this case, rotating about y. So I could say that's going to create a larger problem. Well, not a large problem, but a problem. Because now if I'm rotating about the y-axis, my interior radius is going to that one. I'll always call my interior radius R1. The exterior radius is going to the parabola. That's going to be my R2. So I can go in here and say, if I took a cross section here, if I took a knife and just sliced into this, I can see that those slices are going to be horizontal slices. So it's going to look more like this. It doesn't have to be that flat, but it'll be something like this. And I know that this slice is going to have a certain thickness, and that thickness is going to be a change in whatever my y value is. If you rotate about the y-axis, the thickness of your slice is going to be in terms of y. If you rotate about any vertical axis, the thickness of your slice is going to be delta y. So I'll say, okay, here's my axis of revolution, which is just x equals 0, which is the y-axis. So you need to go from there to here for R1. Well, R1, that's going from x equals 0 till this is the line y equals x. What I need to make sure you see is that you cannot put x for R1. Instead, you put y. Because x is y, I need this in terms of y. There I go then. Okay, so R2. What's the distance from the axis of revolution to the outer one? Well, same thing as I have labeled here. That's from x equals 0. Notice how I'm always saying x equals here. X equals 0 till x equals what? You cannot, so I called it y equals x squared up there. That doesn't work. Solve it for x. X is equal to the square root of y. So you say the length of this radius is from x equals 0 till x equals the square root of y. Square root of y. Now again, keep in mind, if this were any other axis of vertical axis of revolution, the way you would be thinking about it is you're saying, okay, so literally what he's doing is since the curve is to the right of the axis of revolution, what he's doing is he's saying the y value of the curve, x equals the square root of y, minus x equals 0. Exactly, that's really what I'm doing. I'm saying minus the axis of revolution, but it's just 0 in this case. If I were revolving about x equals -1, I would say minus -1. Minus -1 there. Okay. So now, I have my two radial lengths. The area of a cross section is pi times R2 squared minus R1 squared. So I'll say pi times the square root of y squared is just y minus y squared. So the volume of a particular cross section is going to be pi times y minus y squared dy. Then I can say, if that's the volume of a cross section, then the volume of the entire region, no problemo. Now this is going to be a volume function in terms of y, of course. So the volume in terms of y is equal to the integral from where y starts in this region to where y ends in this region. Now that's the only bad thing about this example is if you mess up and choose your x limits of integration, you still get it correct, which is bad. But the reason I'm choosing 0 to 1 is because the y value here is 0, the y value here is 1. I could easily change that up on a test and say between x squared and 2x or something like that. So now, this is going to give me, I'll pull the pi out, y minus y squared dy. We'll get pi times the group y squared over 2 minus y cubed over 3. Evaluate from 0 to 1. When you evaluate it at 1, you get 1/2 minus 1/3. That's 3 over 6 minus 2 over 6 is 1 over 6. Thus our answer, pi over 6. Is this okay so far? Okay. Now, before you start to think that, wow, this isn't too bad at all, we're going to run into, but let me just show you the limitations of this. What if we ran into a problem that had this? And I don't even want to put a function for it yet, and I'm not going to number this, not number 6. We're not going to work this problem, but I want you to realize this method has serious limitations. What if my curve f of x looks something like the following? And I say, take this curve f of x from this point A to this point B and rotate it. Good luck with that, because what's the problem? It's all the same curve. How are you going to find, and now if I say rotate it about the y-axis, how are you going to rotate this about the y-axis if that's all the same function? Your R1 and R2 are coming from the exact same curve. What in the world would I do in that instance? The washer method fails miserably. It doesn't work. So we have to come up with other techniques. And what we're going to be seeing, I'll just go ahead and give you a preview. What we're going to be seeing next week is saying, well, when the washer method fails, we used what's called the cylindrical shells method, and everyone hates it. What is the cylindrical shells method? It says, okay, instead of doing the washer method, put infinitely many rectangles within this region. Rotate every single one of these rectangles about the axis of revolution, and you get a cylindrical shell that results from that axis of revolution. You're going to sum up the volume of every shell from where the shells begin to where the shells end. So that's what's coming. Okay, but now that's the next section.
That sounds miserable. I don't want to do that with my life.
No. So I just didn't want you to think, wow, this washer and this method, it's going to work for every single problem. No. I have to make nice problems in order for you to allow the techniques of this section to work. Okay, so I'll say rotate that same region from number 3, what I'm trying to test today is that you understand it doesn't really matter what axis of revolution, you can account for it. So I'm going to say rotate the same region in number 3 about the vertical axis of revolution. Let's go out there. X equals 15. Why not? Now this is going to be a horrendous looking figure when you think about it. You're like, wow, okay, I'm taking this little piece and revolving it around. So the volume of the object that we're rotating with respect to the hollow part in the middle, pretty microscopic, but it's still going to make kind of like a halo-like object. So I can say, well, okay, when I think of that, I'm taking this region from 0 to 1, and I'm saying, okay, way on out here at x equals 15, that's your axis of revolution. Okay. So we're going to have an interior radius R1. We'll have an exterior radius R2. And they're both going to be extremely long with respect to the region that they represent. That's okay again. So I'll say, if this is, my 15 kind of got mixed up with my dashed line. So that's x equals 15. So I would say, well, I know that my cross sections, once again, the middle part almost eats up the entire region, probably much more so than what I have drawn. But I'll say this is a rough sketch of one particular cross section. So I'll say, I know I need to hollow out this interior radius 1 from the exterior radius 2 I have here. So I'll say, I know area of a cross section, once again, is going to be pi times R2 squared minus R1 squared. In this problem, that's going to give me pi times the second radial length squared. That's going to be 15, oh, sorry, I started to say 15 minus x, but no, because the thickness of my cross sections are with respect to y. So this is y equals x, which is x equals y. This is x equals the root of y. You must think of it in those terms. So I'm going from x equals 15, which is the vertical line at x equals 15, all the way down to x equals y for the outer radius. 15 minus y. And I know that that's going to give me a positive value for the radius because the y values in this problem range from 0 to 1. So it's saying, okay, what's the largest this outer radius will ever be? When y is 0, this radius is 15. What's the smallest this outer radius will ever be? 14, 15 minus 1. So I can say, okay, that's going to account for the outer radius. And it's important that you see, we had a problem earlier where I had to say the functions taken away from 2 because the axis of revolution was above the region. Same thing here, since the axis of revolution is to the right, it would be subtracted from it. Whereas if over here I'm subtracting the axis of revolution from the values, here literally I'm saying the square root of y minus x equals 0. Okay? So that you have to keep that in mind. Minus here, R1 is going to be 15 minus the square root of y, quantity squared. And so I can say the volume of this region is going to be pi times the group. This first one's going to give me 15 squared 225 minus 15y minus 15y minus 30y plus y squared. And then I'll have minus the group 225, so that part's going to cancel. And then I'll have 15 on the root of y, 15 on the root of y, minus 30 on the root of y. And then the root of y times the root of y is going to be plus y. We're taking that entire thing and multiplying it by the thickness delta y. So some simplification, I'll say this volume of arbitrary cross-section, 225 minus 225 eliminates. I'll have y squared minus 30y minus 30 on the root of y plus 30 on the root of y.
Plus 30 on the root.
Yeah, gotcha. And then, ooh, I forgot the minus y in there, so that's actually minus 31y. Need to combine my terms. So minus 31y, and now that does account for all of the values in there. All of this is multiplied by delta y. So now I can see why I did that, because I'll just say I need to integrate from where these y values begin at the region of intersection, y equals 0 to y equals 1. So I'll say this volume in terms of y is the integral. Oh, and I forgot my pi. Boo me. So pi out in front, 0 to 1 of y squared minus 31y plus 30y to the 1/2 dy. Upon our integration, we'll get y cubed over 3 minus 31y squared over 2 plus, it'd be 30y to the 3 over 2 times 2/3. 30 times 2/3 is just going to be 20. And all of this evaluated from 0 to 1. Again, it's nice that 0 is one of our limits of integration. 1 is our other. So I just plug in a 1 and I'll get pi times 1/3 minus 31 over 2 plus 20. Negative 31 over 2 plus 40 over 2. That's going to give me positive 9 over 2. 9 over 2 plus 1/3. That's the same thing as 27 over 6 plus 2 over 6, 29 over 6. 29 pi over 6 should be our answer. Gorgeousness. Okay. Wow! Look at that! Perfect timing today. And I did, everything except the diagonal axis of revolution.
Dark.
Okay, but yeah, that'll be good.